Okay, so okay, good afternoon. So last time we introduced the notion of the greatest common divisor of a pair of integers. Definition 2.3, the greatest common divisor is, as it says, the largest integer that divides into A and B. We looked at some examples, and we proved a very nice result, which I kind of think is the first perhaps non-obvious result of the course, and that the greatest common divisor of a pair A and B, let's call it D for the moment, can always be realized or expressed as a linear combination of the A and B with integer coefficients, the M and N being integer coefficients. We prove that with the aid of the so-called integer division algorithm, or integer division with remainder process, which was in theorem 2.2, and this established that we can always, given a pair of integers A and B, as long as B is non-zero, we can always do our best to divide A by the integer B. It'll go in a certain number of times, this Q quotient, and there'll be a remainder left, which might be 0, but we can always do the division as much as possible and arrange that the remainder is small, meaning that it is size, that the remainder is a positive quantity that's strictly less than the absolute value of B. Okay. So you divide A by B, typically A would be the large number, B the smaller number, so you divide A by B, it goes in a certain number of times, that number of times is Q, and you're left with possibly a small remainder, although the remainder might be 0, in which case we have nice, clean divisibility that B divides A, and you found that A is a multiple of B. And this idea, this concept of integer division with remainder was what we used in the proof of theorem 2.3, that the greatest common divisor can always be realized as a linear combination of the two integers. Okay. Now what we're going to look at today is the Euclidean algorithm. And the Euclidean algorithm is the solution to this kind of problem here. What's the GCD of these, what's the greatest common divisor of these two integers? Okay. So we don't know at the moment, okay, because these numbers are far too large for us to have any intuition about. We don't really want to go ahead and start doing loads of arithmetic with those numbers or looking for divisors of these numbers because the possibilities are huge. So we'd like some nice systematic algorithmic way to answer this question about what the greatest common divisor of these two is. Okay, so how are we going to do it? So the first observation is in lemma 2.4. Lemma is just a name that we use for results which aren't important, aren't as important as theorems and maybe don't deserve the word theorem. So they're a little preparatory result or ingredient result that's needed for something more flashier or more substantial. So lemma 2.4 says if we have integers a, b, and r in this kind of relation, and this is the kind of equation we'd have if we performed an integer division of a with remainder r. And this lemma says that the greatest common divisor of the pair A and B, whatever it may be, is exactly the same as the greatest common divisor of B and R. Okay? So we'll prove that, and then we'll meditate on its significance. This is the real key to the Euclidean algorithm and the key to the solution of the problem of finding greatest common divisors of arbitrary pairs. Okay? Now, I haven't really gone into the proof. Yeah, but it's really just, it comes immediately from one of the properties we have about divisibility already. So if we suppose for a moment that C divides A and C divides B. So suppose we've got a common divisor of A and B. But then we'll also know that C divides R, since R can be written as A minus QB, which is a linear combination of A and B. And remember, we've proved a theorem. Part 3 of theorem 2.1 says if you've got any common divisor, any number C that divides A and B, it automatically divides every linear combination of them. Where the coefficients of the linear combination, here 1 and minus q, where the coefficients are integers. So if C divides A and B, it automatically divides R. Thus, common divisors of A and B are also common divisors of B and R. Okay? So all the numbers that are common divisors of A and B, those same numbers are also common divisors of B and R, if it's the case that A equals QB plus R. And the same goes in the other direction. Secondly, if you've got a common divisor of B and R, then C divides A, since A is equal to QB plus R. So, sorry, the justification was theorem 2.1, part 3. Okay. And run the same argument the other way. If you've got a common divisor of B and R, it automatically divides A. Okay? Because A is a linear combination of B and R. Yes?
Sorry, just the beginning of the proof, what's the lesson for divide R?
That's C with a kind of with a too long lead in. We call it a tail because it's on the lead in, but yeah, so it's just my handwriting C. Sorry, script C. So, and this is for the same reason. This is by theorem 2.1 again. Okay. So the similar conclusion, common divisors of B and R are also common divisors of A and B. So if you divide B and R, you must also divide A. So if you're a common divisor of B and R, you're a common divisor of A and B. So what have we showed there? We've showed that the pair A and B has precisely the same common divisors as the pair B and R. Okay? The same numbers divide both pairs. So in particular, the one we're really interested in, the greatest common divisor of AB is the greatest common divisor of B and R. Agreed? It's the end of the proof. Okay. So this is, I want everybody to understand this clearly before we proceed, because it's the key to how the Euclidean algorithm works.
You said there by theorem 2.1, secondly, if A divides B and A divides R, then C divides A? Or that,
No, if C divides B and C divides R,
and then C divides
then
A,
C divides A.
where is that?
Because A is a linear combination of B and R. Okay. Any other questions about that argument?
I don't understand how that proves that there's the greatest common divisor. Like, surely you just proved that like one divides everything. Like, I don't understand how you prove that that's the greatest.
So the proof comes in two bits, right?
Yeah.
First off, we say any common divisor of A and B also divides R.
Yeah.
So that means common divisors of A and B are also common divisors of B and R. Okay?
Like all.
All of the common divisors of A and B are also common divisors of B and R. Yeah? Common divisors. Yes.
All of them.
And then we go the other way. Any common divisor of B and R must also divide A. So the common divisors of B and R are the same as the common divisors of A and B. So the pair AB and the pair BR have common divisors, and they're exactly the same. So in particular, the greatest common divisor of each pair is the same.
But why R? Because R is a remainder. How could it be?
How could it be what?
How could it be like in that argument? You know what I mean?
There's no reason why it can't be. R is a integer.
You say greater common divisor of A and B is greater common divisor of B and R.
Yep.
How could it be true?
Because R is...
remainder is
Okay, so this question is, R is a small quantity, R is the remainder, so how could its greatest common divisor be the same as, but the greatest common divisor B and R be the same as A and B? Well, you see, I don't think the fact that it's small is any objection. I mean, the greatest common divisor of A and B has to be less than or equal to A and B. Okay, R is no greater than B because it's a small remainder. But that still doesn't mean, it can't have the same, that a common divisor of A and B must also divide R. Okay, so we'll be seeing this in operation soon. So once we have this result then, so consider the problem of finding the GCD of any pair A and B. Okay, we're tasked with finding the greatest common divisor of A and B. A and B could both be huge integers. Okay? We can do integer division of A by B, and we get a remainder R, which is strictly smaller than B. But this GCD of A and B that we're looking for, it's also the greatest common divisor of B and R. So a very important observation here, the pair BR is a smaller pair than the pair AB in general. Because we've replaced one of the numbers. I mean, typically when we do these integer divisions with remainder, kind of A is the large number, B is the small number. It goes in a certain number of times with a certain remainder. But instead of dealing with the pair AB, we can now deal with the pair BR. But we've got rid of the large number A, and instead we've brought in a new number R, which is smaller than B. So the pair BR is smaller than the pair AB. It's easier to deal with. So we've replaced a hard task, i.e. finding the greatest common divisor of A and B, with a slightly easier one. Namely finding the GCD of B and R. Now that's great. If you come across a simplifying move in any problem, if you can replace some problem with a slightly easier version, well, that's good. You've made your task easier. And the Euclidean algorithm turns on this idea, and it involves us repeatedly applying this idea. So we start out asking for what the greatest common divisor of a certain pair AB is. But then we move to the smaller pair BR. Then we just do the same thing again. Next, we're going to divide B by R. We'll get a new remainder, which will be smaller still. And then we can move to that pair and keep on reducing the things until they get so small. Okay? So let's look at an example. It's already written out in full in the notes, so I won't repeat it. We'll look at it in the notes. So it's example 2.4. So here's the example of a run through the Euclidean algorithm. We'll formally specify the algorithm shortly, but it's more or less fully illustrated by this example and maybe a slightly longer example we'll look at next. So here the task is to find the greatest common divisor of 525 and 90. So rather than deal with 525 and 90, we perform an integer division with remainder. We see that 90 goes in 5 times, 450, with the remainder 75. Okay? So applying the lemma tells us that the greatest common divisor of 525 and 90 is the same as the greatest common divisor of 90 and 75. So we've got an easier task, a simpler pair to deal with. We repeat the process. Now we divide 90 by 75. We find it goes in once with the remainder 15. We apply the lemma again. The lemma says the greatest common divisor of 90 and 75 is the same as the greatest common divisor of 75 and 15. So our pair is smaller still. Now we take 75, we divide it by 15, and we find it goes in 5 times the remainder 0. Okay, we've reached divisibility. We apply the lemma again. It tells us that the greatest common divisor of 75 and 15 is the same as the greatest common divisor of 15, which is the B position, and R, the remainder. Greatest common divisor of 15 and 0. And what is the greatest common divisor of 15 and 0? So remember, we proved that everything divides 0. So the largest number that can possibly divide 15 and 0 is the largest number that can divide 15, because everything divides 0. So the greatest common divisor is 15. Okay. So the final version of the problem has an immediate answer. The greatest common divisor of anything non-zero and 0 is whatever the first number is. Okay. So we found a greatest common divisor. 15 and 0 is 15, but it's the same all the way up. Okay. So 15 is the greatest common divisor of 525 and 90. So that shows you the Euclidean algorithm working. Let's jump to another example, which is just illustrated over the page. We'll be saying more about it shortly, but so here the problem is to find the GCD of, 1, 2, 3, 7, 8, and 3054. Okay. What's the greatest common divisor of 1, 2, 3, 7, 8, and 3054? Well, we perform integer division with remainder. We find a remainder 62. So applying the lemma tells us that this is the greatest common divisor of 3054 and 162. Still too large to know what it is, so we do the integer division with remainder again. We divide 3054 by 162, we see a remainder 138. So this is the GCD of 162 and 138. Okay. So we apply the process again. 162 divided by 138 gives a remainder 24. So this is the GCD of 138 and 24. Do the integer division again, we get a remainder 18. Do the integer division again, we get a remainder 6. And do the integer division remainder again, we get 6 and 0. And the GCD of 6 and 0 is 6. Okay? Because everything divides 0, and 6 is the largest number that divides 6. Okay? So the final answer, the final GCD can just be read off. It's just the first argument. So you see I put a little underline there. That's another way it's articulated. The last non-zero remainder. The last non-zero remainder in this process is the GCD of the original pair, well, of all the pairs you've met down through the running of the algorithm, but not the original pair, which was the original problem posed. Now, is this an algorithm? So an algorithm, to be properly called an algorithm, your method has to have two main properties. It must be unambiguous, okay? There must be no, it must just follow automatically. There must be no, it must be capable of being programmed onto a computer, okay? Well, that's okay. We're given the original pair. We perform integer division with remainder, and then we perform another integer division with the b and the r we got from the first one, and we keep repeating that process. So it will be possible to specify this in computer code, okay? It's not ambiguous around. So that's the first property an algorithm must have. It must be very clear and unambiguous, and you can turn it into computer code. The second key property an algorithm has to have is you have to be sure the calculation process will end. Okay? That's desirable as well. I mean, that's quite important in the theory of computation. We don't want to be giving our computers tasks which we're not sure if they're going to possibly end. We're happy to wait around a long time to allow the computer to do the complicated calculation, but we have to be sure that the process is going to end. Okay? Now, will this process end? Well, there's a very appealing and a very satisfying argument that proves to you that this process will always end, is that the remainders you're seeing are getting smaller each time. Okay? And they're bounded below by 0. So we've got a decreasing sequence of integer remainders that are bounded below by 0. So that means there can only be a finite number of integer divisions in this process. Because the remainders are getting strictly smaller each time, and they can never go below 0. So that means they must eventually hit 0. So after a certain number of integer divisions, we will see the remainder 0 appear, and then the GCD will be the last non-zero remainder. Okay. So that is the Euclidean algorithm for finding the greatest common divisor of a pair of numbers. Okay? Any questions about it just at this stage for finding the GCD? Now there are exercises there. You will be tasked with doing this by hand and carrying this out by pen and paper a few times, and it's definitely a good exercise. It's definitely a good exercise to do so that you're familiar with how the algorithm works. But the main thing here is to know about the existence of the algorithm as something that we can hand over to the computer to do. And hopefully in a few moments I'll show you how we do that. But the Euclidean algorithm does a second thing. it also produces the so-called Bezout's identity. Now, Bezout's identity, remember we proved this result that the theorem 2.3, the greatest common divisor of a pair A and B can always be realized as a linear combination of A and B. Well, such an equation, a linear combination of A and B, which gives you the greatest common divisor, such a thing is called Bezout's identity. Okay? And we can actually extract that from the Euclidean algorithm as well. See, theorem 2.3 just proved that this kind of thing existed. It didn't give you any kind of an algorithm for constructing it from a given pair A and B. But that is present in the Euclidean algorithm. Okay, so we can see this working here as well. If we look at this example we just stepped through, 6 is the greatest common divisor of the original pair, 1, 2, 3, 7, 8, and 3054. Okay. What we seek is a linear combination of those two numbers that is equal to that greatest common divisor. Okay, these linear combinations, these Bezout's identity are useful in cryptography and useful in number theory. And it's good that Euclidean algorithm can give them to us. And we can construct them. We can find these coefficients, the 132 and the negative 535. We can extract these from the sequence of integer divisions that we've just done. And we do it by working backwards through them. So if we look at the second last equation, which featured 6, the greatest common divisor, as the remainder, if we make 6 the subject of that equation, we get 6 expressed as a simple linear combination here, 24 minus 18. But one of those numbers is the previous remainder, the 18. Okay? So we can take the previous integer division with the remainder and use that to express 18 as a linear combination of 1, 3, 8, and 24, one of the previous pairs. So we can replace the negative 18 here with 138 minus 5 times 24. Okay. Now we don't do any arithmetic evaluation of this here because it will just collapse again down into 6, which isn't, and then we'll have proved 6 equals 6. So congratulations. But so you don't want to do that. You want to preserve the linear combination. So look, you've got 24s here, and you've got plus 5 more 24s. So in total, we've got 6 24s and minus 1, 138. So now we've got a linear combination of the pair 24 and 38 equal to 6. But then you look at the previous integer division with remainder. It can express 24 as a linear combination of 162 and 138, the next pair up. So you use this equation to replace 24 with 162 minus 138. Okay. Again, collect terms in this equation that you have now. You've got 6 162s and minus 6 minus 1 138, so minus 7 138s. Now, at this intermediate stage, we've expressed the greatest common divisor, 6, as a linear combination of this intermediate pair, 162 and 138. So we just keep repeating that process. We keep working backwards through the integer divisions with remainders so that we next get 6 as a linear combination of 3054 and 162, and make a final substitution, and we'll get 6 as a linear combination of the initial pair. Okay.
Where is the minus 7 comes from?
The minus 7 comes because we've got minus 6 times 138 minus another one. So in total, there's minus 7 times 138. Yeah?
Yes.
Yeah? But just what you want to avoid doing is you want to avoid actually evaluating, because if you evaluate that bracket, you just go backwards to 24. Or if you ever did evaluate the whole thing, you just go straight back to 6. That's not where you're trying to get. You're trying to construct these coefficients, the 132 and the minus 535. Okay? So I've skipped out the last couple of stages, but the next process you do is you would use the second equation to replace 132 with the linear combination of 3054 and 162. And then use the first one to replace 162. To finally give you the linear combination of the original pair. Okay? So we now know that Euclidean algorithm can give us two things. Okay? It can give us the greatest common divisor of any pair of integers, and it can also, by working backwards through all the integer divisions, it can construct an example of Bezout's identity. Okay? A pair of coefficients which, when multiplied by the original pair, give you the greatest common divisor. Now, what we've got there in algorithm 2.1 is a formal specification of that. Okay? But it's just putting into formal general language just what we've seen in those two examples. Okay? So I'd encourage you to read through that and appreciate that formal description of it. But it really is just giving a general description of what we've seen in those examples. Now, there's a few more corollaries here after it, which we might discuss next time. And there's various end of chapter exercises. You'll see I ask you to do pen and paper examples of the Euclidean algorithm a number of times to get good practice with it. There's also a set of intermediate exercises. If we go back to exercise 2.1, and I just want to do one of these for you now, which is question 6 from there, because it's kind of hidden away in one of the exercises, but it's an important result by itself. So this is called Euclid's lemma. So the name Euclid is featuring a lot today. So we suppose a number C divides a product A times B, and that we know that the greatest common divisor of A and C is 1. Which, remember, that says that really A and C share no divisibility properties. They don't share any divisors at all, apart from the trivial divisor 1, which divides everything. But yet, if we have this assumption that C divides the product AB, if C has nothing to do with A, the conclusion is then that C divides B. Now this will be an important tool, the important tool, in proving the uniqueness part of the fundamental theorem of arithmetic. Remember, the fundamental theorem of arithmetic is the theorem that says that every positive integer can be written as a product of primes in a unique way. Okay? One and only one way.
Would be an important tool in
The uniqueness part of the fundamental theorem of arithmetic. Sorry.
It's kind of just
Yeah, you can see it now. I've said it.
Yeah.
UNIQUENESS. In the uniqueness part of the fundamental theorem of arithmetic. We've already proved the existence part. We've already proved, using induction, that every positive integer can be written as a product of primes. It just comes out from the definition of a prime number. So what we're not sure of yet is that those factorizations are essentially unique. Okay? But we will be able to prove that, and it's Euclid's lemma which is the key part of that. So what's the proof of Euclid's lemma? Well, this comes from comes from this idea of expressing the greatest common divisor as a linear combination of the two numbers. So since the GCD of A and C is equal to 1, that means there exists a pair of coefficients m and n such that this greatest common divisor 1 is equal to m times A plus nc. Okay, so that comes from theorem 2.3. But the greatest common divisor can always be expressed as a linear combination of the two numbers. Now we're trying to prove that C divides B. So what we want is, at the very last line of our proof, we want to show that C divides B. So in other words, we want to be able to express B as something times C. At the moment, we're up to this stage, that 1 is equal to n times A plus n times C. We also have this assumption that C divides AB. So we would also know, say, that AB is equal to QC for some integer Q. That's what it means for C to divide AB. So we've got this linear combination, and there's a very neat way that we can introduce B into the situation. We want an equation with B on the left-hand side. Here we've got an equation with 1 on the left-hand side. So we can simply multiply both sides of this equation by B. So B is now equal to MAB plus NCB. And we're trying to factorize C out of this. We can see a C here, and we see an A times B here. And we know that A times B is a multiple of C. So by substitution from above, we see that B is equal to NQC plus NBC. Just reorganize that. So B is equal to NQ plus NB times C. So that's our integer that does the job. Okay. Okay, so this is just, okay, at the moment it just looks like a neat little result about GCD, and when you've got a number dividing a product, and the number C is co-prime to one of the factors in the product, then we know it must divide the other factor. So this will, in a lecture or two's time, we'll see this more or less proving the fundamental theorem of arithmetic for us. But I just wanted to give some prominence to that, so at the moment it's hidden away as exercise 6, or question 6 in exercises 2.1. Okay, so for the next tutorial, this is most of the exercises are open up to you now. So everything in exercises 2.1, everything in exercises 2.2, page 15, and more or less everything in exercises 2.3. There are some things there mentioning the least common multiple and so on, which we'll do at the head of the next lecture. But basically all the exercises are now available to you. You just read through the rest of the material in section 2, chapter 2, but I will cover it in the next lecture. So what I'd just like to end with today is just to show you how easy it is to implement the Euclidean algorithm. Okay? I can show it to you in Sage or MATLAB. would you like to see? MATLAB. MATLAB, I guess, is what you're using most. Some of you. So it should come up here. I was actually just doing this. Okay, shh. Okay, I was actually just doing this before the class just to refamiliarize myself with the syntax of writing functions in MATLAB. So you write a function in MATLAB by using, so here I've opened up a script file, MATLAB.m file. You write a basic function by using the keyword function. Then D is going to be the output of the function. And you equal to my GCD is the name of the function. And then you list the arguments to it in brackets there. Now remember, we described the Euclidean algorithm as working by repeatedly applying the process of integer division with remainder. Now what that means for how it's implemented in computer code is that you have something called recursion. So recursion in computer programming is the process where you define a function, but you're allowed to use the function itself as part of the definition. So you see here that I'm defining a function called myGCD. And in the course of it, I seem to do something contradictory, is that I use the command myGCD. And that normally would cause a problem. Normally, you shouldn't be allowed to define something and then use the thing you're trying to define in the definition. But it's okay in a process like this. You see that the program just consists of one if statement. So if this condition, do this. Else if this condition, do something else. Or else if neither of those conditions hold, do the last thing. But the first two conditions just deal with the cases where one of the inputs is 0. Remember we said when we met that GCD pair, the GCD of 6 and 0, it's automatically 6. Okay, because everything divides 0. So the GCD of 0 and b, that's the case where a is 0, will automatically be b. The GCD of a and 0, that happens when b is 0, the GCD will automatically be a. So if either of those cases happen, the output of the myGCD function will be the corresponding thing, b or a. It will be the correct GCD. But in all other cases, we instead call the very same function myGCD on a new pair. And this is the pair b and r. So this quantity here is actually r. Remember we had the integer division a equals b cubed plus r. So we have r is equal to a minus b cubed. This q, this quotient, is what you get when you call the function floor of a divided by b. The floor function, have you met that before in MATLAB? The floor function, the floor of x. When you call the floor function on an argument x, it gives you the largest integer less than or equal to x. Okay? So floor of 10.5 is 10. Floor of 20.1 is 20. It's the largest integer less than or equal to the argument that you give it. So we give the floor function the argument a divided by b, and that will give us out this integer quotient q. So when we do a minus the floor of a divided by b times b, that gives us the quantity r. So then we can use this function that we've just defined. Give it any pair of integers, and it will run through itself and give you the GCD at the end. Okay? but it's an appealingly simple little function. Okay, there's just a couple of zero cases to check for. Otherwise, you call the function again on the new pair, on B and R. Okay, so it's got a very elegant implementation. That's a pity you asked me to do it in MATLAB, because actually you can see when I was testing it out here, if you try calling it on very large integers, MATLAB complains, because MATLAB has a hard upper limit on the largest integer it can deal with by default. Sage is slightly better. Sage can deal with arbitrary integers, subject to the physical capacity of the computer itself that Sage is running on. So whatever the hard memory limits of the largest thing it can hold in its memory, but Sage is actually quite adaptable and it can deal with arbitrary sized integers. Okay, we'll leave it at there for this evening. So work away on all those chapter 2 exercises and we'll deal with them in tutorials next week.